All right, today we're tackling a classic thought experiment from the world of computer science, and it's got a bit of a philosophical twist. It's all about a dinner party that could, in theory, go on forever. So get this. Is it actually possible for 5 of the smartest people in the world to sit down for a meal and all end up starving? It sounds completely absurd, right? But the answer to that question reveals a really deep challenge in how computers handle tasks. To really get our heads around this, we first need to set the scene for this very strange dinner party. Okay, so picture this. 5 philosophers are sitting around a big, round table. In the middle of a table, there's a giant bowl of rice. Now, here's the catch. Between each philosopher, there's only 1 fork. So 5 philosophers, 5 forks. And these folks only ever do 2 things. They either think really deep thoughts or they eat. Now, there are some very specific rules for this meal. To eat the rice, a philosopher absolutely needs 2 forks, the one on their immediate left and the one on their immediate right. And it can't just snatch them both up at once. They have to pick up one and then pick up the other. Once they're done eating, they politely put both forks back down and go back to thinking. Seems pretty straightforward, doesn't it? So we have our little story, but let's see how this quirky puzzle actually represents something way bigger than just a hypothetical meal gone wrong. At this point, you're probably wondering, okay, why are we talking about hungry philosophers? Well, this isn't just some brain teaser. It's a perfect, real-world metaphor for a core problem that all operating systems have to solve. And this is where it all clicks. In this analogy, each philosopher, well, that's like a process running on your computer. Think of an app or a background task. The forks? Those are the limited resources that process needs. Things like access to the CPU, or a chunk of memory, or maybe a network connection. And eating is just the act of that process using the resource. The problem, of course, is that you don't have infinite resources, just like our philosophers don't have infinite forks. So how do we manage this? Well, computer scientists came up with the tool that, at first glance, seemed to solve the whole problem perfectly. They used something called a semaphore. The easiest way to think of a semaphore is like a digital occupied sign. Each fork or resource gets one. If its value is 1, hey, the fork's free, come and get it. But as soon as a philosopher picks it up, the value flips to 0, signaling to everyone else, sorry, this one's in use. So the logic, the code, would go something like this. A hungry philosopher runs a wait command on their left fork. That flips its semaphore to 0. Then they do the same for the right fork. Once they have both, they can eat. And when they're full, they run a signal command on each fork, which flips their semaphores back to 1, making them available again. And you know what? This works. It totally prevents 2 philosophers sitting next to each other from trying to grab the same fork at the same time. It seems like we've designed a perfectly polite, totally orderly system. But have we really? Because this is where our perfect solution reveals a catastrophic hidden flaw. There's a digital trap just waiting to be sprung. Let's think about the absolute single worst moment this system could possibly encounter. What happens if every single one of our 5 philosophers decides they want to eat? At the very same instant, their programming kicks in, and they all perfectly execute the exact same first step. Following the rules, every philosopher reaches out and picks up the fork to their left. In that instant, every single semaphore for every fork flips from 1 to 0. They are all now occupied. So, now what happens? Well, each philosopher is holding 1 fork, and now they're all waiting for the fork on their right. But the philosopher to their right is holding that fork, and they're waiting for the fork on their right. And it goes on, all the way around the table. Nobody can move, nobody can eat. And that, my friends, is deadlock. It's a digital gridlock where every process is waiting for another process, and the whole system grinds to a complete and permanent stop. The philosophers will just sit there forever, holding 1 fork, waiting for a second one that will never, ever be free. They will literally starve. Okay, so that's a pretty grim outcome. But luckily, there are some very clever ways to make sure this dinner party disaster never actually happens. Let's look at 3 of the most common fixes. We can escape this trap in a few key ways. We can limit the number of participants, we can change the rules for how you grab the resources, or we can just break the symmetry of the whole situation. The first solution is probably the simplest. Just don't let all 5 philosophers sit down at the same time. If you only ever allow 4 philosophers at a table with 5 forks, then even in the worst-case scenario where they all grab their left fork, there will always be 1 fork left over on the table. That guarantees at least one person can get their second fork, eat, and then free up their resources for everyone else. Problem solved.
Another way to fix this is to just change the rules of the game. You make it so a philosopher is only allowed to pick up forks if both their left and right forks are available at the same time. No more grabbing one and then waiting for the other. It's an all-or-nothing deal, which completely prevents that circular waiting pattern from ever starting.
But maybe the most elegant solution of all is to introduce a little bit of asymmetry. What you do is you number the philosophers, and you tell the odd-numbered ones, 1, 3, and 5, to pick up their left fork first, then their right. But you tell the even-numbered philosophers, 2 and 4, to do the opposite, pick up their right fork first, then their left. That one simple change completely breaks the fatal symmetry. The system can never get stuck in that deadlock spiral. It's really quite brilliant.
So, the dining philosopher's problem isn't just about code, is it? It's a fantastic model for resource competition everywhere. It really makes you wonder, from traffic jams where 4 cars all want to enter the same intersection, to political standoffs, where else do we see these principles of deadlock trapping us in our own lives, just waiting for a resource that someone else is holding?